So I just have some quick announcements before we start. So I wanted to thank Texas Instruments for providing the venue. Also, I would like to thank IEEE Signal Processing Society and the Communication Society of Santa Clara Valley for sponsoring the event. And I want to thank our volunteers for helping us arranging these events. So first, I'm Mehran Nekui, chair of the IEEE CIS SCV. Ami is the vice chair. Rajesh is the secretary. Priscilla is the treasurer over there. And Yuju and Reza are program coordinators. So thank you. So we are looking for more volunteers. As you know, this is the chapter. The topics are very hot these days. So if you want to know more people, get more involved, please come talk to us or send us an email. This is a great opportunity to be more involved. Also, if the companies you want to sponsor us, get to more visibility for your company and get people to hire more qualified candidates. There are some great opportunities to sponsor our events. Please talk to us or send us an email. So there is an announcement by San Jose State University for a future event, and then Reza will introduce the speaker. He will be chairing the event today. Thank you.
Hi, everyone. My name is Maral. I'm part of SJSU BMES. So every year, SJSU BMES holds a biomedical device conference where we bring industry professional and students to speak at that conference. So this year's theme is Innovations Through Diversity, which is, I think it's a really cool theme. So this is a great opportunity for you guys to network with other industry professional and with students. So if you guys have any questions, I'll be sitting over there. The date is March 28th, but early bird registration ends on March 16th. So if you guys have any questions, I'll be sitting in the back over there, and I have save the dates and flyers, so pick those up. Thank you.
Hello, everyone. My name is Reza Daj. I am a coordinator. A little background, I guess most of you know, deep learning, deep neural network. Some of the scientists, engineers, and practitioners in this area think that artificial intelligence is the fourth revolution in the human history after agriculture, industrial, and internet. And a lot of these thinking is based on what deep learning and neural network has done over the last 10 years. Now, one thing in neural network is that we have a lot of calculations. And for that reason is what GPU is very important. And so whenever we can cut some of the things that are not important, like we have a sparse network, or we have a matrix that some of the elements are not important, then we need to keep them, but at the same time, we have a lot of space that are not really being used. So what the speakers is going to speak for us tonight, and I have to say that we are very glad to have a women speaker. Today is the International Women's Day. And so it's a great pleasure to have a women speaker tonight. So Helen has a fantastic bio. I guess if you had the chance to read some of it, she has got his bachelor and master's degree from Tsinghua University, that is probably the best university in China.
Yes.
In her opinion, and she has got the PhD from Purdue. And after that, she worked at Qualcomm, Intel, Seagate, and for some time at Pittsburgh University, and then eventually moved to Duke University, where she is now an associate professor. Well, we are very glad to have you here. And I'm going to stop talking and give the microphone to you. And please welcome, join me and welcome Helen.
Thank you. Thanks, Razi, for a very nice introduction, and thank you all for coming here. I'm very happy to be able to giving this talk, especially on this very special day. But trust me, I didn't plan on this. So today I'm going to talking about the running sparse and low precision network. As Razi introduced, I came from Duke, and we have a center called Computational Evolutionary Intelligence. So basically, we have about 25 plus PhD and postdoc, students and working on the area, starting from the devices to circuit designs to system implementations, as well as in some algorithm improvements. So today I'm going to introduce a bit of our research, and if you have more questions, welcome to visit our website, and we are like to talk more about and communicate more about this topic. So, as usual, whenever we're giving a talk, people will say, okay, why don't you talk, the motivation of the work? I kind of feel this is so obvious, but still, I give a few pages slices about that. So, in fact, the concept of the neural network is not new. It has been there for many, many years. Even we do not have to go back for very long histories. As you can see, the convolutional network was proposed in the 80s. And of course, at that time, the concept was there, but the computer itself, the hardware itself wasn't that ready, okay? So even at a situation that theory is advanced than the hardware configurations, unfortunately, the research on the neural network kind of jumped into a dark period for many reasons. Personally, I think the problems like vanishing gradient cannot be supported because of limited precision in the execution. Because people at the time actually observed that even we adding more layers, it doesn't improve the performance much. And of course, later on, we figure out this is just because the hardware doesn't support enough or sufficient layer or structures. And again, by the end, I believe this is because we do not have high performance computing devices. CPU is really good, but at the time, the computation speed was not enough, was not high enough, and also CPU was designed for general purpose, not for the vector design. So the situation changed things about 2006. Hinton's group starting using GPU to running the networks. And then people find that, okay, such kind of a vector-based operations is very efficient. And then, another round of AI, or at least neural network and machine learning is actually started. So I actually like those data to show what is the trend, what happened in past years on machine learnings. In academia, for instance, as you can see, this data shows the journal articles mentioned about the deep learning or deep neural networks in past years from different countries. And of course, United States is always leading, but in the past several years, China actually captured and published more. Another thing I really like to present is that, in fact, I started joining the NIPS community only 2-3 years ago. But one observation I find was, first, the attendee numbers, participant numbers increased very, very rapidly. And even so, these numbers was not limited or constrained by the people's pension. In fact, it's limited yearly by conference facilities and allowance, okay? So all levels of the sponsorships are sold out. The situation is very different from a lot of the other conferences, in fact. Of course, we're talking about academia. More importantly, what's happening in industry. So like Sandra talking about machine learning, talking about the machine learning and seeing machine learning as a core transformative way by which we are rethink everything we are doing And examples could be like number of the software projects with the Google that use key machine learning technologies. And as you can see the trend, I only have data by 2015, but it grows really, really fast, okay? On the right side, in fact, is the industries or organizations engaged with the NVIDIA on deep learning, okay? So actually, I had some old data before, like 2013, there are only about 100 organizations. And of course, the pace increased so fast. So if we only counting from 14 to 16, it's more than 10 times increase. And if you trace back to 13, that's a hilarious number, I believe. Well, okay, since I came to San Jose, the Silicon Valley, so I guess people must talk about the stock. And obviously, I'm not good at the financial stock, so I just grabbed this page of information over here. So people talking about stock is in true measurement about what's going on, what's the interest, what is the technology. So believe it or not, if you're looking back on 90s, companies working on the PCs, their stock performance is pretty nice. And then afterwards, you can see that the feature phones company captured a wave. And in the past, about the 10 years, in fact, smartphone-related companies like Apple dominate the market. But if you're looking at what happens on GPUs for deep learning, okay, the past 2 years, it goes really, really fast. And probably that's indicating, or it can be taken as one indicator that deep machine learning is a trend. And of course, I was here only half an hour so far, and everyone say, okay, right now every person, every company, everywhere is talking about the machine learning and the artificial intelligence, okay? So probably we're truly starting entering this new regime. So next question, usually people will ask is why deep learning is so hot right now. I guess we are actually merging into a time that we have a lot of applications and generate a lot of data and also require a lot of data to do the analysis. And we also having algorithms, maybe not fundamentally explain the truth about those algorithms yet, but we do have many ways to do the learning. So our advances in algorithm innovations, not only about the neural network, in many other ways actually leading better accuracy in a lot of cognitive applications. And of course, my background, again, is from hardware. So the third very important reason, I believe, is the innovation or the progress in the hardware in semiconductor area, which really started from this area, from Silicon Valley. Okay. So talking about our group, I briefly mentioned about our center and our group. We actually also trying to working across of all the layers, okay? So one of the reasons is, and it's really, really very difficult to separate it and just to focus on one task. So if you really wanted to know it and get to familiar and really make contributions, you shall have to explore all the opportunities. So we work on the hardware, algorithm, and applications on different things. So today I will majorly focus on the a few works on the algorithms and touch a little bit about the hardware to say they actually kind of related, not separated. Okay, so here is my outline. So I made some change after, passing the information to our chairs. But basically today I'm going to talking about 3 examples of our research. The first thing is, in considering the situation like lightweight computing engines, kind of cannot afford a very large DNNs on the edge devices, okay? That's the fundamental constraints in many, many situations. So we proposed the structurally sparse DNNs. Essentially, it's trying to simplify or reduce the parameters and computation requirements of the networks and still provide sufficient accuracy to the applications. The second example is talking about the communications. So besides computations, the data transportation is another, very critical constraints, okay? So in this example, we're talking about the distributed learning. So in the learnings, it's like when we're putting a lot of the students or the workers to learn something, the communication in between becomes very critical. And we propose 10 grand to quantize the gradients and therefore reduce the communication cost. So truly talking about that, my background is on the hardware levels. So in fact, our lab's doing a lot of works on new architectures for future computings. I guess many people here heard about the term of the resistive memories or memory stirrers. We actually dedicate a lot of efforts trying to develop new computation engines by using this new technology. And I'm going to give a few pages, briefly talking about this. So first of all, the structurally sparse deep neural network. Well, whenever people talking about the neural networks, usually it's starting from such kind of structures. Okay, as you can see, we say this is an original structures with the fully connected between neurons. Okay, so obviously there are a lot of connections in between, indicating a lot of weights parameters, and also many neurons, and indicating a lot of activation functions. So previously, people trying to reduce the model cost, computation cost. So techniques like pruning the synapse or pruning the neurons and essentially reduce the model size. So this is actually Professor Sung Han's work in 2015. As you can see, for this network with the 5 convolutional layers plus 3 fully connected layers, okay, they are able to reduce basically a lot of number of the fully connected layers. The parameter reduction on the convolutional layers is not so visible because comparably, convolution layers contributes more to the computation instead of the data storage. But pruning or sparsifications has been proved like it can significantly reduce the storage size of the DNNs. And also people talking about that if we have a customized hardwares, it can help to improve the execution performance as well. However, what we find is we ran the methodologies, okay, on the CPU, on the GPUs, on the general computing platforms, okay. As you can see, through the 5 convolutional layers, the sparsification rate actually remained very, very high, very close to the original papers. However, when we ran this on different hardware platforms, okay, we do not really see the speed up projected by the original authors, okay. And in fact, for a lot of the cases, we didn't benefit. We sacrificed the performance. So we're trying to understand what was the reason. The reason is when we use random sparsifications or prunings, your data becomes too non-structured, meaning data doesn't show a very well localities. And therefore, I mean, if you have background on the hardwares, you know the data access becomes really difficult. You probably need encoding and decodings to get informations. And those all kind of contribute the cost in the execution. And therefore, if you're looking from outside the black box, actually you do not see the real benefit at all. So I can also further show you our experiments on the CPUs. Basically, if we do the original sparsifications, this is the map of the matrices. So black dot shows this is non-zero element, and the white shows it's a 0 elements. So visually, you can see that many, many weights can be removed. But since this is what we call the not structured, okay, so the performance improve on CPUs is better than what we can see on GPU. However, if we are able to achieve such kind of sparsity, this is our work. It's kind of remove the entire rows or columns completely. And then you can imagine that entire matrices can be squeezed into a very dense, smaller sizes. The execution efficiencies can be dramatically improved. Okay, this is the concepts we proposed. So what is the structurally sparse deep neural networks? Okay, basically what we expected is, and we are able to remove the weight or the connections group by group. Okay, not individually, not in very, very small grains. So a group can be a rectangle block, a row, or a column. Okay, even the entire matrices, if we say this layer is not necessary at all. So, so back to like the CNNs, people always talking about the CNNs. So what can you do? So this is the structural illustration of the CNNs. So we actually can remove the channel. We actually can remove 3D filters or 2D filters. We actually can remove a filter shape fibers, and this actually corresponding to in columns in matrices, in weight matrices. Or, I mean, like ResNet have done, we actually can remove entire layer if we prove this is not necessary in some cases. So how do we do this? In fact, the methodology is so simple. What we basically do is to apply group lasso regularization, and this is all you want, okay? What do I mean? Basically, with the weights you have, you can define, okay, and group them, okay? So for example, for 5 parameters, we can separate them into 2 groups. For each groups, we apply the group lasso. So basically, we have like a squared of the, sum of the, a square root of the sum of the square cases. And then we kind of sum them all, and we apply this as part of the regularizations. So this is the original minimization functionalities, and we apply the group lassos with a certain coefficiency. So this is all we wanted to do, and we refer this methodologies as a structured sparsity learning methodology. So usually we receive the question and say, okay, why such kind of simple methodologies can work? Okay, so if you're looking at the gradient-based structures, basically this is a group of weights, and we usually apply, according to the loss functionalities, we apply this when trying to update the weights, right? So this part is taking as the regular gradients to minimize the error. And this is the part we introduced through the group lasso, okay? So if you're looking at group lassos, essentially, this actually shows the same directions, and this actually trying to push this to the zeros. So what we're trying to do is, if we find out, or during the trainings we find out, this group of the parameters is not so important, the approach of this, we're trying to minimize that and pushes to the zero or close to zero. All right, so I mean, if you like to have more details of the methodologies, you can reference our paper, but I like to show you some efficiencies of our methodologies. So this actually shows the structure sparse applied on the AlexNet, okay? There are so many data. For example, if we can allow 2% of loss, this shows the performance and statistics for the L1 norm methodology. This is the original sparsification methodologies proposed at algorithm level. And this part shows the structure sparsity learnings proposed by our group. Basically, those numbers shows the speed ups compared to the baselines on CPU or GPU runs. And as you can see, original methodologies, though the sparsification remain very, very high levels, the speed up numbers isn't very, very high, especially for GPU runnings with high parallelisms. So if you compare what we obtained on CPU and GPUs, it's a lot of higher than L1 norm, okay? I mean, we also run the situations without losing any accuracy. And of course, in this cases, the performance improvement is a little less. So on the right part actually summarize the overall speed up of the CNNs running on different platforms. The left 3 groups shows the results from GPUs, and the right 4 is from the CPU runs. and TA421 representing the thread numbers. Okay, so on the left side is more like high parallel runnings, on the right side is less parallel runnings. And no matter what cases, actually we wins in the situation. So we also actually apply in trying to do structure sparsifications on ResNet. ResNet has been known because it can bypass entire layers, right? So what we're trying to see is, through our methodologies, are we able to further remove more layers? And does it make any sense? So basically, we use ResNet 20 layers or 32 layers. I believe this is for Cypher. So as you can see, with the similar error rate, we actually can further reduce the layer numbers. Of course, it's indicating lower implementation costs and a higher execution efficiency for performance. All right. So there are more situations. Actually, we also investigated, okay, what is the possibilities when we apply that to RNNs for long short-term memories, okay? So here, the illustration shows a structure in the LSTMs, okay? So basically, the observation is, okay, as you can see, this is the input. It's go through the structures, okay? And this is the upper layers. So basically, the structure shows us as all the basic structures must have the same dimension, okay? So basically, when I remove like one line like the white direction illustrated over here, we have to corresponding to remove all the corresponding entries along the structures. Okay, you couldn't omit one because otherwise the consistencies between layers will be broken. Okay, so it's indicating that the sparsification for the LSTMs is even harder because everything is correlated. We couldn't do independent removal for the case. All right, so actually what we observed is, okay, maybe I shall explain a little bit. For the structures, it's corresponding to like 8 matrices operations over here. So basically what we observe, like if we find one hidden input is 0, and of course the corresponding input over here, okay, this is useless because your input is 0. So supposedly you're able to remove the entire rows, okay? And the removing of this actually will result, okay, it's output over here. I mean, this part is going to be zeroed out. And this will be served at the input of another layer, right? Or the next round of the iteration. So it's indicating that it's corresponding to, horizontal on the, input related matrices, okay? And also, if we see the output over here is zeros, okay? If you're looking back the path, the corresponding runnings over here, okay, they are also not necessary because your output is 0. So the corresponding entries on the matrices can also be removed. This is the essential basic idea of our methodology. So by doing this, we actually run some applications, and this is the application learning access sparse state from scratch in stacked LSTMs, and it has 2 layers. It starts a baseline with 1500 by 1500, okay? And the top part actually shows, like, after applying the structure sparsity learnings, what is the matrices look like? And of course, you can imagine originally everything over here will be full up, okay? The upper layer, since we have 10,000 outputs, so it's really long and we do not have to show everything over here, okay? So what I want to show you is some comparisons, okay? So if we keep the similar validated and testing perplexity, the similar accuracies through our methodologies, actually we can quite significantly reduce the elements in the LSTMs. And the weight number reduced like only 1/3 of the original designs, and the execution speed actually is really improves. Okay, that's our major contribution. And of course, you may ask, why don't we start training the LSTMs initially from a smaller network? For example, through our experiments, we know this is probably in a better, configurations. Why don't we set up the LSTMs like this way and start trainings, right? So starting from the directly designs with these parameters, of course, the speed up will, compared to the baseline, is still quite significant. But if you're looking at perplexity numbers, the accuracy numbers, actually it's not that impressive. So basically, if you're starting from a bigger network and trying to shrinking to a smaller one with the proper structured guidance, okay, this actually can help to develop in dense networks with high, accuracy and efficiency. Yes.
So, is the size reduction the difference between running at memory speeds and running at last level speeds?
What's the speed?
Memory speeds. Almost all references end up going to memory. And when you densify the network, almost everything fits in a 3 megabyte or 32 megabyte.
That's actually one of the motivations of our work. So essentially, people trying to move the models and also a lot of intermediate calculation results on chips, so you do not have to suffer from the high memory access latency. This is one thing, but we didn't start from there. This is actually is a benefit, we say, and later on, I have a few slides to show when we implement on the FPGAs, this becomes our major concern. Okay. Of course, there are a lot of experiment results. I do not like to talk too much about that, but essentially we get more examples on LSTM applications, and it's always benefits. Well, our work was published on NIPS 2016, and afterwards, actually, many people actually followed our work. Okay, so I just give 2 examples. This is an OpenAI. They recently have this block sparse width and sparsifications. And basically, what they're trying to do is kind of doing the sparsifications by blocks, and they actually obtain a lot of performance improve. Another example is the DeFi. This is Chinese and machine learning acceleration companies. They recently on CVPR workshop 2017 to show like we could start from irregular matrices to neural networks and go to the right. And especially they mentioned that the vector level sparsity is not only going to help to improve what we're talking about the memory accesses, computations. In fact, such kind of regularized structures is also helpful in the storage, because indexing of such kind of structures, matrices is a lot easier than kind of compress or index and random sparsification structures. Okay. Talking about the hardware-related designs. Okay. So of course, majority of the algorithms were first evaluated and understand at the GPUs, okay? But we also trying to understand what is the impact on the hardware levels. And of course, GPU or CPU is not sufficient. So one of our related work is trying to develop some design frameworks on FPGA-based accelerators, okay? So imagine, okay, there's some startups or there are some small IoT devices and trying to leverage neural networks. What is the best design? And this is something we're trying to explore. And very importantly, what we wanted to understand or develop is there any better frameworks or methodologies to automate the entire processes? So on the left, as you can see, this is the basic frameworks we have. So the key things is over here. So basically, when we're developing these frameworks, okay, the hardware configurations, okay, or the constraints will be fed into the tuning processes. In tuning processes or training processes, we're giving some certain configuration tables back to the implementation. Okay, and this implementation configuration tables will also affect, the implementation details. So usually it takes us several rounds of iteration to reach the best performance. So of course, as you can see that we take a longer time to training because we have to consider what we have on the hardwares, okay? On the right part, in fact, is the basic structure we developed on the FPGAs. So essentially, we're trying to create a uniform structure. So our designs is we call the process element-based designs. So within each PEs, okay, we of course have a PE controllers, and we actually have local kernel buffers and feature banks, and a certain max were used for the convolution computations. And of course, afterwards is ReLU and the maximal. And DMA controllers and engines is used, and also global control units is used to, distribute the data, because of course it's for the FPGA board we have, it's very, very difficult to always to, have an entire networks to feed into one board. I mean, we have a lot of data to show, but of course, we couldn't present everything over here. So one thing I want to show you over here, in fact, is, okay, through our frameworks, we actually can create different network configurations for different hardware, purpose. So, for example, still talking about the sparsifications, as I previously mentioned, the convolutional layers actually requires a lot of computation resource. And the fully connect layers actually, major demand is on the model parameters. So it basically consumes the storage and also, of course, the communications whenever necessary. Okay, so for the hardware platforms giving to us, okay, if we have some critical design parameters saying giving the accuracies, we could prove more and remove more parameters on the convolutional layers. We also could do transfer the efforts on the fully connect layers. So our design efforts sort of framed us, in fact, to find out what is the best ways to trade off the computation requirement versus the memory requirement. And through this ways, we are able to maintain the accuracy, but trying to balance the computation and also data accesses. Okay. Well, this page basically shows the comparisons on our works compared with the previous FPGA implementations. Okay. So, of course, there are so many data. The only thing I want to emphasize over here, in fact, is the practical G-flops. So, as you can see, the practical G-flops of our work is kind of comparable and lower than the previous implementations. But we benefit from the sparse network. We doesn't have to be so fast as the previous work. And if we're really talking about the time per image processing, actually our access is a lot faster and more efficient than the previous work. And this is the essential goal of our work. It's kind of a software and hardware co-designs. Okay. This is actually conclude my work on the structure sparsity learning. The second example I want to present, as I said, is about the communication cost. So our typical example in this area is ternary gradients in distributed deep learning. Okay. So let me start from this. So let me, okay. I mean, there's an animation. So basically, distributed deep learnings is because right now people trying to developing bigger and bigger neural networks. And of course, the training becomes really headache. So we're trying to have more workers, more machines to do the task. So for such kind of implementations, what people usually do is we can probably apply the synchronized data parallelisms for the stochastic gradient descent, SGDs. So what do? Usually the first time is we distribute the training data, we split the training data to n subsets, considering we have n workers. And then each worker going to have one model replica. So as you can see that the model actually is kind of local. Everyone has a piece of the model. And then each replica is trained on, just a subset of the data, okay? And of course, then different models will be trained in different ways because the input are different. So eventually, those models are going to send and synchronize their trained model, parameters to the parameter servers. And parameter servers collect all the data from all the workers. And then once they finish the collecting, they average, for instance, and distribute back to all the workers. So now every worker is on the same page and they can restart next batch trainings. So of course, when we have get an army of servers working on the same network trainings, and each of them only get a subset of data, the computation cost or computation time reduces significantly. However, you also can be observed that there's kind of exchange of the gradients and also the weights distributions. So it's actually increased the communication requirement. And of course, this is very common, like networking problems. You have more workers, and then the communication costs really increase in an exponential way. Okay, so we were thinking about that. Is it possible to reduce the cost of gradients? Maybe we can make it really simple, like ternary gradients, like it's only 0, +1, or -1. Okay, that's like 1 or 2 bits data, and then we are able to, reduce the communication cost. So in order to do that, support the situations, we made a big change in the distributed learning assumptions. So remember previously, we actually passed the gradients to the parameter servers, average, and distributed the weights to all the workers, right? So in other words, instead, we each worker submitted the gradients, and here the parameter servers average, and then they send out the ternary gradients back to the, they send the parameters back to the workers. And the worker, of course, can do the local calculation about the weights, okay? And they all remain the same. It's the same thing, okay? Since we transfer our methodologies to ternary gradients in this ways, communication cost can be reduced. Okay, so there were a lot of questions in this work's theory part. For example, we're trying to understand what's the difference of this, we're trying to explain what's the difference of stochastic gradients, why our work is working. So basically, the stochastic gradients is kind of a randomly pick or drawing the gradients from the set of 1 to n, set of the gradients, okay? And the expectation over here is, and the change of here is the same as the cost function change, okay? Since it's, imagine you have a lot of, pieces, and every time you randomly draw that, so eventually, stochastic space, and we can take it as the same effect. So our change actually is, besides randomly draw from, these pieces, we do the ternarize. And we expect, or we hope, the expectation over here will remain the same, okay? So how do we really do this? I mean, on the left side is mathematical representations of our methodologies, but I'd rather use the right side examples to explain that. So essentially, if we got a layer of the gradients to calculate like these factors, okay, we actually have a scalar. Of course, we have some calculation ways to get this as scalar, okay? And then it's translated to, this is translated into the scalar and the signs of those gradients, okay? So how do we pick, those bias or the gradients? In fact, the probability is calculated by the real number of the gradients divide by the scalars, and we take it as a probability. And then we use these probabilities to generate the possibility, not bias, the gradient possibilities. And then the sign actually is remain as the previous values, okay? So as you can see, when we do this, okay, originally you have a layer, and you have weight matrices or vector of the gradients to transferred between the parameter servers and also each workers, right? Right now we reduce this into one scalar and a vector of 0 and also +1 or -1s. Okay, so obviously the communication cost reduces quite significantly. We also, made a lot of assumptions, and I mean, this is very theory, but essentially what we wanted to say is standard SGDs truly converge, truly converge under, the 3 assumptions listed over here, okay? And our assumption, in fact, is slightly stronger than this, and during the trainings, we're trying to maintain this is true. Okay, so as far as this is maintains true, the stronger boundary retains truth, and then we are able to, obtain a good effects. Okay, so during the practice, in fact, we made a lot of, engineering kind of tricks, okay? One of the trick is saying, okay, when we do the tenorizing, so, okay, remember I have a scalar, okay? So instead of to have an, global scalars for every layers, what we find is the gradient distribution or the weight distribution across layers are very, very different. So a better way, in fact, is to pick the most optimized scalars for each layer. So we call layer-wise the tenorizings, okay? And the second part is, okay, when we pick out the scalars, okay, the gradients, we do not like it has a very long tail, okay? So sometimes we got difficulty of this. So instead, okay, like what I say, the convolutional layer and fully connect layers, here is the distributions of the gradients through the iterations. So instead of the long tails over here, we're actually giving clipping values. Okay, I can talk about this. So whenever it's exceeding the clipping values, we actually made it as the maximum and minimum boundaries. Okay, so this actually related to the 7.3 in the previous page. So we're trying to, force this to satisfy the stronger, boundary conditions we proposed. Well, following kind of some results. Following is kind of some of the results we obtained. I guess my time is really limited, so let me quickly explain this. Basically, as you can see that this shows the results on small networks like LINET. And this methodology shows that through different workers, the accuracy remains very similar. So, this also shows that compared to the floating work and our training cases, no matter we have 2 works or 16 workers, the drop of accuracy is not that much. Okay, it's tolerable. Okay, but I guess most of you are more interested in talking about the larger networks, right? So what we find is, the 10 grand basically is trying to inject in some randomness, okay, and regularizations, okay? So basically training processes for the large networks, we have to considering what we injected, the randomness and the regularizations. So therefore, we actually made some changes. So usually in the trainings, so we take dropout and take it as made the activation more random, right? So in our cases, we actually apply a smaller dropout rate, in order to kind of balance and compensate what we obtained from the 10 grand. Also, we use smaller weight decays, okay, because we already consider certain regularizations, okay. So just quickly talking about this, as you can see, for different cases like mini batch 256, the top 1% accuracies, it doesn't change much. And if we grow to like 1,000 workers, in fact, our work kind of a slightly performance better than the original work, okay. Well, there are like even more like results. On this page, basically I want to show you like for the Alex trainings with the 4 workers along the iterations, as you can see, the top line accuracy trend is very similar and consistent to the baseline, okay? And of course, here is the training loss versus the iterations. They all remain very similar as the baselines, okay? And on the right side, actually, as you can see, we actually have very similar accuracy as the original. But communication cost is reduced, and therefore the training efficiency actually a lot of higher. So this is the last page results I want to show you. So if you, looking into this, every 2 bars is in one comparison pair. The left solid one is the original designs, and the right part is our 10-grade methodologies, okay? So it's starting from like 1 worker to 500 workers. So here we want to give a few summaries or our observations over here. So basically 10 grand gives high speed ups if there's more workers. It's so obvious, right? Because we reduce the communication cost. And of course, if the communication bandwidth is low, we get more. For example, our paper also have the results with the InfiniBand. I mean, if we increase the communication speed 100 times, of course, the benefit for our work wouldn't be so obvious, but still we gains, okay? Training DA with more fully connected layers. For example, if you say here, the green bars shows the results of the VGD nets, okay? Of course, it's very slow because it has a lot of fully connected layers, requires a lot of gradients exchange. But if you compare the difference of these 2 bars, it's very, very high compared to the other bars for the same reason. It's essentially talking about the more parameter exchange needed, and then the more benefit of our methodology is, okay? So at the end, I mean, I do not have a lot of time. I also want to mention a little bit about RM-based neuromorphic chips designs in our lab, okay? So I think I got questions like, do you still working on the hardware? Are you completely moving to the software levels, okay? I like to say that hardware is essentially very, very important. My background is hardware. My background is on the non-volatile memory designs. And in recent years, non-volatile memory-based new computing approaches is also massive, a lot of work on this. I just give like scattered examples on different layers, on different applications, on different non-volatile memory technologies over here, okay? Why particular RAM in our labs? Well, frankly speaking, I mean, when I started working on the non-volatile memories, I work on the magnetic and RAM. And obviously, RAM is easy for matrices operations, and then we pick it. But later on, I do find there are a lot of advanced features of the RAM technology. So for example, it can use for spike time dependent plasticity. So yesterday I was at Intel. They recently formed the neuromorphic computing lab, and they're actually trying to do very biology-based training process, neuromorphic chip designs. We also recently, I mean, we have been working with the HP labs for quite years. And recently they find out chaotic dynamics can be controlled. And then we actually trying to leverage this, chaotic dynamics in training, and which can quite significantly improve the training efficiency. Well, the right part is basically saying like multi-level cells, like very high resistance versus low resistance ratios. Those actually all kind of advanced features of RAM for the neuromorphic computing. So what we really do on the chip levels, okay? So this is a very lower level details. So imagine you have such kind of a crossbar array structures, and if you injected voltage or spikes along the input directions and collecting those spikes vertically, okay, it's basically a matrix-based computations, okay? And of course, the situation wouldn't be so easy as I illustrate over here. So for example, one obviously difficulty we find is, okay, so assuming this is the theoretical some of the matrix operations, right? And y-axis show the output process generation. So ideally, we expect linear relations, and our measurement, in fact, doesn't look so nice. It's a nice curve fitting, but it's not like nice linear functionalities. So essentially, we're facing a lot of physical constraints, like circuit operation speed, plastics and so on and so forth. So our labs are putting a lot of efforts in trying to understand what is the weight mapping structures. Okay, how can we improve the implementation accuracies? How do we deal with the low yield of the RM currently developed? So one example, for instance, when we're talking about the RM technologies, majority of company effort is still as in memory. So it doesn't take like analog states. So when we're doing the network designs, are we able to do the quantization and the mapping the weights? Again, what is the best ways? In fact, over here, we apply the structured learning methodologies over here, certain ways, and trying to regularize the training processes, and therefore we are able to capture the right weight distributions and map to the not very reliable RM arrays. We're also trying to have understanding that what if the neural network is very large? That is common case, but on the other end, the arrays we obtain is very small. So we have to partition large arrays and remapping to smaller physical arrays, and how can we improve the utilization ratios. So one way over here is to do the low rank approximation, okay, but traditional low rank approximation doesn't benefit a lot. Traditionally, you do the trainings, you do the low rank approximations, and then you test it. You suffer from the clipping errors. So what we do is, again, we're trying to implant the low rank approximation into the training processes. So in this ways, during the entire training processes, the accuracy remains as high, but rank ratio can gradually reduces. Okay, in this way, we actually maintain the accuracy, but also have a good, high utilization ratios. Here, this page basically show our chip designs. It's kind of hard to say, but basically here is our controllers. Where's the array? Yeah, and here is our arrays, and we're putting them together. We have a new version recently, have everything vertically integrated together, but we do not have all the data is finished yet. Okay. Well, okay, I guess 1 minute to the clock 8 o'clock. So just a quick summarize the perspectives. Perspective, I think AI becoming mainstream. It's not like I'm talking about this. Everyone here is talking about this. So majorly, I think because it's showing potential on both cloud and edge. However, we have to say that the infrastructure, the hardware part, okay, still is kind of the limitations, okay. Second, I think future AIs will be more useful, user-friendly, more automatic, more cost-efficiently. Basically, it can ease our life efficiently. I didn't talk much, but our lab right now working on the security of AIs. I guess with a lot of data surrounding us, there's a lot of networks surrounding us, and a lot of mobile and different devices can be easily accessed. The data securities and device securities becomes a very, very large issue. Okay, so at the end, this is not only me, and this is done by our entire team. I actually bring some students over here. We actually is working on the algorithm levels. Sicheng actually working on the hardware levels, and Xiaoxiao graduated from our labs before, and she is working on the networking levels. Okay, so I hope we can further discussions. They can answer a lot of detailed technical questions with me. At the end, I also like to acknowledgement all the supporters, including our universities, federal agencies, and also our collaborations at industry. So that's all I have for today. And one thing I want to further emphasize is this is our lab webpage. So it shows more information about our research. Of course, we have so many students. It's not only about the 3 topics I present over here. So welcome to visit our webpage. And if you have any questions or interested, we are very happy to talk about that too. Okay, thank you very much. Yes, please, Dave.
You had a graph that showed 3 different kinds of norms, the normal L1 and L2, and then one that was kind of jagged at the bottom.
Yeah.
I didn't quite catch what that was all about.
Okay, sorry about this. And I was kind of in a hurry and didn't explain that very well. So essentially in the RMs, what we find is, so the question is, and for the RM-based designs, the regularization functionalities we applied is not like what people usually use, the L1 norm or L2 norm. We actually have this jagging shape to do that. So the reason is, and we find is in RM technologies, people can provide like high resistance, low resistance. People can provide like 4 levels of resistance, okay? So it's kind of individual separate levels. So we were thinking that if we are able to quantize the values to those individual, levels instead of have a wide analog distributions, then when we do the mapping on the physical arrays, the situation can be a lot easier. Okay, so L1 norm, for instance, can generate a lot of zeros. Okay, and distribution of the weight will be kind of something like this. Okay. And since we have several options, and then we apply this kind of a Jagged seesaw type regularization, okay? And this will, for example, for fully connect layer 2, original weight distribution is illustrated like the bar over here, the blue bar over here. And through our methodologies, it becomes to very obvious, 3 values, okay? So this is ways we kind of modify the softwares and according to make the hardware design easier or kind of put hardware constraints into that. Yes?
Thanks for the great work.
Thank you.
I have 2 questions about the structural sparseness. One is there are many model design try to put some structure in the model structure. I wonder if you have tried some of the newer model, for example, Google's mobile net, whether that you can see the same speed up. That's one. The second one, is open-ended. So you're trying to use your method to really reduce the computation. Is there a way to apply to do it reversely to increase the performance rather than just reduce the
performance in terms of
reduce the computation right now, right? It's the same network, same structure. You try to reduce the model size while retaining the performance. But is there a way to apply it to the reverse? Say, I don't care about the model's complexity. I just want to increase the model performance.
Like accuracy.
Yeah.
I see. I don't recall we do anything trying to improve the accuracy. I'll be always trying to maintain the accuracy. Accuracy improvement computation is very difficult because that's really the major focus from company. Okay, so I guess this is one thing. And regarding your first question about the Google's lab?
Yeah, the mobile net.
Mobile net, we didn't do that, did we? Yeah, because the work was done in 2016. Yeah, so at the time, a mobile net wasn't there, so we didn't do for the mobile light. Yeah.
Sorry, I didn't quite catch it. How do you decide the groups in the first section of the structural sparsity?
Oh, yeah, that's a very common question, in fact.
Is that a manual or an automatic process?
Sorry, a lot of what process?
Is that an automatic or a manual process?
Well, you can see that it's still some manual process involved because, for instance, you decide to do channel-wise the sparsification or decide to do sorry, I got lost. Like how shape-wise the sparsification. So you have to define that. So I call this as a manually part of it. Like basically, what is the final shape of your matrices? You have to think about that. And then you actually decided how to group it. It's all correspondingly. And then the following operations will be automatic.
And then if you're removing specific inputs, isn't that essentially building in, like structurally building in overfitting into the resultant models?
I didn't get the questions. Remove a part of the inputs vectors or the entire inputs? I didn't get it.
Right, you showed an example where you're moving like a row and several columns. And if that goes from one of the inputs, so that input never has a result.
Oh, I see.
It's sort of like overfitting on your
Oh,
data
I
set
see.
there, right?
Yeah. So corresponding. But as you can see, when we do the sparsifications, the first layers, actually, you do not see very high sparsification. This is basically the first layer is trying to get tiny features. And then when you propagate it, this becomes very, very obvious. This is true for probably all the sparsification methodology. Yeah. But that is true. Yeah. Oh, okay, sure.
I think it's more clarifying what the other person said. So you said you manually remove certain things.
Oh, sorry. I was looking for you. Sorry about this.
You manually remove certain things.
No, we do not manually remove that. We manually apply the regularization constraints. Like we manually decided what groups define, how to define the groups.
Okay.
Yeah, the training itself is automatically. It's just like how the trainings we had.
And how is the selection? So from that algorithm, the regularization algorithm makes the network sparse afterwards. Once you group them,
yes.
And then the decision is made after the
Yes.
lasso regularization.
Yes. Okay. That's true. Yeah, thank you. So yeah, okay, again, so we manually decide the groups, the ways to generate the matrices or the expectations, like you want to remove the entire row or you remove the by columns or both, okay, together or one by one. And then you do the trainings, yeah. Mm-hmm.
So do you apply the sparsity to the training or just the influence only?
Do we apply the sparsity to the training? So I think we apply the groups definition in the trainings, and then eventually it's generate the sparse the networks. So it's affect the ways to do the training. That's yeah. Okay. Did I answer your question? Sure.
So in your second section, so you assign those weights to each robots that you assign the gradients that you apply to the scale you apply to the gradients, and then feedback to the robot. How do you define individual scales?
Oh, that's very, very good questions. Basically, we analyze the distribution of the gradients. We take 2.5 times of the deviation, I believe. So generally, we take it as the range of the maximum and the minimum. Okay, so anything beyond that, I just complete that to the minimum and maximum. Yeah.
But when you apply, how do you define which scale goes to which?
Which scale goes to which layer, or which layer? I mean, define the value of the which layer, right? Am I right? Uh-huh.
So you're saying that you assign each individual have different scales. You are not using a universal.
Oh yeah, each layer has different scales. Yes. So in each layers, like layer 1, we have 1,000 parameters, right? So 1,000 gradients. So 1,000 gradients, literally, you can form in distributions: the mean, the max, the minimum, and the maximum, the deviations. Right, so we basically decided based on the deviation. So we calculate the standard deviations times 2.5. Yeah. So I guess your next question is ask why 2.5, because that's very common. Yeah, many people ask this. Yeah.
Hi. So I've been listening to how you talk about your work. And what I notice is that although you do performance optimization and power optimization on your networks, you don't use those terms very much. Could you explain why you don't use those terms?
Power optimization and
Performance optimization.
performance optimization.
So you go faster, yay, and you take less power to get the same answer. So, I mean, other people in different would say, we're faster and we're cheaper, yay.
Oh, I see, I see. Well, yes, yeah. I guess I'm not good at marketing, and that's why I haven't had my own startup yet.
Well, so part of the reason I'm asking is, since you have some experience in Silicon Valley, because you worked at Intel, right? So it's not like you never heard of what I'm talking about, right?
Yeah.
But it is indicative of, that the culture you're working in doesn't like to think in those terms. And if that's true, why don't you tell us a little bit about the culture?
Oh, so I mean, you just asked about this question. So for instance, you really want to jump to the neuromorphic designs or FPGAs. I use more like cheaper, like lower power, or those kind of terms. But the first two works is actually we started from software levels, from algorithm levels. So a lot of times I present like today's, the expectation is many people actually are interested more at algorithm levels. So my language is shifting to usually, those audience.
Okay.
You know what I'm saying? But our group's effort, in fact, is trying to bridge the software level and the hardware level.
Yes, very nicely.
Like separately or isolatedly. Thank you. Yeah, this is a very good suggestion. I didn't really think about it and pay attention on this. Yeah, thank you.
Hi, Helen. So when you quantize the gradient into -1, 0, and +1, you're just saying that the magnitude of the gradient is not important, only the direction of the gradient is important. Is that correct?
The direction is obtained by the sign.
Yeah.
So we have the scalar, we have the sign, and the 1 or 0 or -1 was determined by the original value.
And you multiply back with the scalar.
And multiply by the scalar. So how do I decide like a 1 or 0? Basically 1 and 0, because I already have the sign over there, right? 1 and 0 is kind of stochastic generations. The probability of 1 and 0s is determined. The probability of the 1 and 0 is the same as the original value.
I'm just wondering, if you applied it to the single GPU, the ternary gradient, what will happen? Will it increase the training time or decrease the training time?
I have to ask a way to answer this question, then that's too detailed, I guess.
Single GPU? So in this work, basically, is trying to reduce the communication. So if it's just one GPU, then I guess no.
I guess it's talking about the GPU within GPUs.
Oh, you mean the communication within GPU, correct?
I just use the ternary gradient in my single GPU training.
In your single GPU training?
So it will increase the training time or decrease the training time?
I guess the time is similar. It's similar. If your communication of gradients is not a bottleneck, then no.
we can double check. Double check. Yeah.
Hi.
Yes.
Yeah, B again. So
Sure, welcome.
So earlier in your talk, you had a talk about neural net pruning, right? So I was wondering, have you neighbored with your biological colleagues to find out if life is imitating art or art is imitating life? Because the pruning regimes you show a tremendous reduction that might be very similar to the reduction mechanisms that happen in mammalian brains as people get older. Have you explored that option at all?
Okay, so algorithm levels, we didn't explore that for sure. I mean, we do not find a lot of customers in this area. But how did we start this research on the sparsification and prunings? In fact, we learned the first word, a small world, from neural network and the biological peoples, and they actually passed me the information that infants actually have an a lot of synaptic connections, okay? They have certain synaptic connections, and then when they grown up to the teenagers, it's kind of grow the network. But if a person getting even older, actually a lot of redundant, synapses can be removed. This is actually has been proved by neuroscience people by years experiments. So I guess one of the common incentive is like what we talk about as TM examples, okay? So people like to grow to large network in order to contain more information, in order to, because at the time you probably do not know the capacity of the knowledge, how much you need. So this is how people usually like to start from very large network, training from that. And what we are doing is very similar as the second phase of our life. We say, okay, this is knowledge you're going to learn for your life. You're probably going to learn more, but we do not know. And then we starting trunking the synaptic connections, made it more like lower power consumption, lower energy consumption. Yeah, thank you.
I think it's better that we wrap it up. I think Helen will be here for just a few minutes, so if anybody else has burning questions, then you can come. Yeah, the slides will be provided. Yeah, and so let's thank Helen again, and we also have a token of appreciation that we want to give to you. It's just a certificate.
Oh, thank you. Thank you so much.